Hey, Phoebe is with us.
I'm driving again. I'm sorry, but I'm here.
Well, you be careful.
All right.
All right, let's see. Let's who else we have here. We have it's just you and me, Phoebe, for right now. And
Okay.
I've got 1 minute before class starts, so they're just taking their time is the thing. They'll show up. I put that lab on Blackboard for you guys.
Okay.
Let me write down what that lab is. It's oscillating circuits, I think. Let's see here. Yeah, it's a the lab Thursday night. You know what? That's lab 10. Lab 10, experiment 13, Thursday night, RLC circuits. It's a damped oscillation. Oscilloscope method. So that's what we're doing Thursday night. That's lab 10.
Okay.
Now, the next week will be your makeup lab. I didn't bring my calendar, but we could probably figure it out. Today's the 9th. No, today's the 10th. Thursday's the 17th. The 24th will be the makeup lab. I wonder if anybody missed any labs. Let me look and see here. We'll see if anybody missed any labs. Yeah? Stephen missed a lab. Brian missed a lab. Nobody else did. Christy, remember Christy? Christy missed a lab, and Chastity missed a lab. Yeah.
So, did we come to class that day? Did we come to class that day if we didn't miss a lab?
I'm just trying to figure that out. It looks to me like I don't think you've missed any. You don't have to come that day. Hey, Nicholas is with us. Hey, Zach is with us. Good deal. Let me see if Zach
I
has
missed
missed
that. I
any.
had a connection issue.
I don't think Zach has missed any labs. So he doesn't have to come if he doesn't want to.
You said about when we didn't miss a lab, whether we come, because I had a connection issue.
Yeah, I would, if you didn't miss any labs, you don't have to come that night. It's a makeup lab. But
Okay,
you're
I was
welcome.
just checking, like, if we had something else that we should do or something.
No, but you're welcome to come. Everybody's certainly welcome to come. But those
Okay.
of you that I mentioned, you should come. Okay, well, we got that figured out. Now let's see what kind of homework we're doing. Then we'll launch into our topic tonight. This is the 10th of November. There is some homework. It's the homework is homework number, let's see, that'd be 12. I think this is homework number 13. And it's chapter 14, problem 41. And it's due Friday. It would be due Friday. Oh, gee, Friday the 13th. That homework is due Friday the 13th. Oh, well. Now, tonight we're studying chapter 14. We really go fast. We do a whole chapter in one evening. And so we need to get started. It's time to get started. But before I do you have any questions for me? Any questions or comments?
So the final is comprehensive, right?
Right. And we're not going to meet for the final. It's going to be a take-home, online final.
Oh.
So you get to do it at home. You should do good. I hope you do.
Okay. So then the last meeting that we'll have as a class would be that makeup lab?
Yes. And
Okay,
some,
just making sure I understand.
yeah, and some people may not even come to that, which is okay. So it might be some people, the last time we'll meet together will be this Thursday night. That's kind of weird, isn't it? But it'll be okay. All right, well, let's take a look at chapter 14. Chapter 14 is all about inductors. There's capacitors. We've studied those. We had a whole chapter on those. And there's resistors. We've studied those. And tonight it's inductors. And we know the symbol for capacitors, it's C. And we know the units, it's farads. And we know the symbol for resistance, it's R. And we know the unit is ohms. And we know well, I don't know if you know, but it's L. They use L for the symbol for inductors. Now, I don't know why they used L. There's no L in the word inductor. There is a C in capacitor, and there's an R in resistors. But they couldn't very well use I, because they use that for current, don't they? But anyway, this is what they use. And the unit for inductor is the Henry. But we've studied that already. You know about Henrys. Well, I think we did it in lab. We studied about Henrys. A Henry is equal to a volt divided by a amp times a second. It's kind of a weird unit. But a volt divided by an amp is something that we all know and love. That's an ohm, isn't it? So Henry's can be expressed as ohm seconds. Okay. Well, the topic tonight is inductors. And let's go back to Faraday's law for just a minute. But before we do, does anyone have any comment or question? Okay, well, I'm going to erase this. You don't need that. It's in your, it's on your blackboard there on your computer. You can look all that stuff up. You can look it all up. All right, Faraday's law. I think there's a whole chapter on that too. And it goes like this. Now, is there an N in that? Yeah, I think there is. I think they put it, in case you have multiple loops, then you have to multiply by the number of loops you have. That's Faraday's law. Now that's magnetic flux. And in case you forgot what that is, magnetic flux, well, the definition of it is B dot dA. It's really a dot product. Some people call it a scalar product. It's a scalar. Did you know that dot products you don't get a vector? See, vector products, you get a vector. If you have something like what's one of our things that's a vector? For instance, we have an equation that goes like this. For dipole moment. Oh, gee, my mind is just mush right now. It's something cross B, right? No, here we go. Yeah, here we go. That's one of our equations that we know and love. It's the equation for the torque of a current loop. That's a cross product. And when you have a cross product, another name is vector product. You get a vector. Torque is a vector. But see, this is a dot product or a scalar product. You don't get a vector, you get a scalar. Magnetic flux is a scalar. Magnetic flux is a scalar. Torque is a vector. That's that little guy that we studied called the dipole moment. It's a magnetic dipole moment. I don't know if you remember what that is, but it's equal to IA, and you make a vector out of your area, and I, of course, is current. But there you have it. There's Faraday's law. Now I want to review for just a few minutes here. I like to review at the beginning some of the important equations that we've had for magnetic field. See, that's a magnetic field. And I'm going to give you this one here. That's the magnetic field for a solenoid. Where this is at, what is it, permeability of free space, number of coils in your solenoid per length, and the current in your solenoid, that's magnetic field of a solenoid. Now here's the magnetic field for a long wire. Some of these equations we have derived from pretty much together using the Biot-Savart law. You remember the Biot-Savart law? Now what this is the magnetic field of a long wire. Now that we mentioned the Biot-Savart law, here, let me write it. The Biot-Savart law goes like this. In integration form, it goes like this. That's the Biot-Savart law. Remember, it was discovered before Ampere's law. I think I told you about Ampere's law. There's also an equation for a short wire. Let me write it for you. The magnetic field for a short wire goes like this. If I can remember how, yeah, here we go. That's magnetic field for a short wire. We even mentioned a toroid. I think I showed you that one night. The magnetic field of a toroid goes like this. And last but not least, the magnetic field for a current loop. Well, this is at the center of the current loop. That's at the very center of a current loop. That's the magnetic field for a current loop. Now, I want you to look at all these equations that we've had before, and they all have something in common. Let me go to one of my wonderful students here. Let me pick on Nicholas. Nicholas, unmute and say howdy, please.
Hello.
Hello. Hey, Nicholas, look at all these equations that we've been studying in this class. They all have something in common. What is it? In fact, they might have more than one thing, Nicholas. But go ahead,
Well,
what do you think?
They all depend on current.
That's it. That's what I wanted to hear.
Right.
They have other things in common. I think they all have this mu sub zero.
Yeah.
Every one of them has that mu sub zero, doesn't it? But they all depend on current. Okay. Now let's see. Magnetic flux depends on magnetic field. And magnetic field, here, let me write this out. Let me write this out someplace. I need some room, so we'll just make us some room here. Magnetic flux depends, it depends on magnetic field. And magnetic field depends on current, just like Nicholas just told me. Every one of these equations, if you make the current bigger, you make the magnetic field bigger. See it? Look, you double the current, you double the magnetic field. Same with all of these. You double the current, you'll double the magnetic field. So the magnetic field depends on the current. Well, if the flux depends on the magnetic field and the magnetic field depends on the current, I got a feeling that the magnetic flux depends on the current too. That makes sense to me. If the flux depends on the magnetic field and if the magnetic field depends on the current, well, then the flux depends on the current. Now here's Faraday's law. So if the flux depends on the current, then this equation here, there might be some kind of constant involved, but you should be able just to go di dt here. Instead of having the change in flux with time, we can just have the change in current with time. Kind of makes sense. But the question is, what is this constant? Well, they decided to call that constant L. And what L is the inductance. That's what our topic is tonight. It's the inductance. And here's an equation. It's very similar to Faraday's law, only it's got di dt rather than the change in flux with respect to time. It's a constant. Once you make your solenoid, for example, the number of turns you have and how long it is, well, then the inductance is constant. Okay, well, if you understand all that, that was a little bit of a review, and now we're gonna take these two and we're going to play with them. Here we go. I'm going to erase all this stuff here. You know all this stuff. And we're going to do a little algebra here. What we've got is minus in first derivative of your magnetic flux equals minus the inductance di dt. Now we're going to do a little algebra. They got minuses on both of those. See those minuses? Why don't we just kick those out of there? We don't need those stinking minuses. In fact, they have a little dt on both of them, don't they? See if you can get to here with me. Do a little algebra here. Were you able to make it to there? Can you get from here to here? Okay. Well, here, try this now. Why don't we go like this? That's just a constant. We can take a little integration there. Take an integration there. And we can go from 0 to some magnetic flux value. And here we can go from 0 to some current value. And here's what you'll have. You'll have N times your magnetic flux when you integrate that with respect to your magnetic flux. And here you'll get L times I when you integrate that with respect to current. And so what is inductance? Well, it's N times your magnetic flux over I. Well, I wonder if that's in your book here. Let's look and see. Look on page I'm shopping around here. Um, well, I don't exactly see that, but it's something very similar to it. What they have is, they do have this on page 640. They have this equation here, and I know you can get from there to here. Okay, well, let's look at the units in that. Or they do have that equation exactly like we have it on page 643, I see it. But I already told you what the units are. The units are henries. But let's see what a henry is. Well, this N is dimensionless. That's just the number of turns you have in a coil. But we know what the units are for magnetic flux. It's Tesla meter squared. And we know what the units are for current. It's amperes. So a Henry is a Tesla meter squared per ampere. But see, a Tesla is a Newton per amp meter. So if you go Newton per amp meter for the Tesla, and you got meters squared over amps, no, that's not right. I did something wrong. A Tesla is a, just a minute here, I'm goofing up here. A Tesla is a Newton, no, it's a Newton per amp meter. Yeah, I think I did that right. And then see, you have, I did that right. Yeah. So you have an amp down here, and so you have a Newton meter you have a Newton meter per amp. Why don't we write that as a coulomb per second? And then we can put our amp there, and one of those meters cancels out. So we have this, and you know what this is? It's a joule per coulomb. That's a volt. I'm running out of room here, but that's equal to a volt second per amp, like I was showing you earlier, and that's equal to an ohm second. So these are all ways of representing a Henry. A Henry is equal to a Tesla meter squared per amp. A Henry is equal to a volt second per amp. It's equal to an ohm second. Yeah, that stuff is all correct. We did great. And now we have our Henry. We know what that is now. So what? Well, I don't know. Let's just see what we can do with that. Any comments or questions so far? Yeah, all right. Let's see where we're going next here. I wanted to show you an LR circuit. We're going to talk about an LR circuit. Let me draw one here. And we'll come up with a lovely equation for an LR circuit. Okay, well, we know a lot of stuff already about inductors. And nobody's asking me any questions. We're going to make a circuit here now. How about this? There's our inductor. And we'll put a battery in here. And then a switch. And a resistor. There we go. We've got a resistor, an inductor, and a battery. And what we're going to do is we're going to do Newton's or Kirchhoff's voltage law around this circuit. This is called an LR circuit. It's an LR circuit. It has an inductor, it has a resistor. Of course, it has a battery too. Without the battery, nothing's going to happen. But when you throw this switch, when you throw that switch, you're going to get current. And the current, which way will the current go? Clockwise or counterclockwise? Let me go to one of my excellent students here. Zach. I'm going to pick on Zach. Zach, which way will the current go in that circuit? Will it go clockwise or counterclockwise?
Clockwise.
Ah, too bad, Zach. You missed it. You had a 50-50 chance of getting that right. What happens is the little pluses are repelled from the positive side of the battery, and they take off and they go counterclockwise, and the current is counterclockwise. Zach, aren't you glad I told you that?
Yeah.
Yeah, you bet. That's important. We got to know which way the current's going. It's going that way. Now, we can get the voltage on the resistor. That's no problem. In fact, we can get the voltage on the inductor. We just discovered that the voltage on an inductor is given by this right here. And I tried to explain it by something depends on something, something depends on something, and whammo, we got ourselves an equation for voltage in an inductor. But let's write the Kirchhoff voltage law. Here we go. This is your battery. And if we go from here to here, that's a plus voltage. And then we go from here to here, that's minus L di dt. That's the voltage there. There you go. And then here, this is plus and minus. You'll notice what the inductor is doing. It's plus minus. It's kind of like, it's acting sort of like a battery that's bucking your battery. Your battery is trying to push current this way. But if you had a battery in there that was plus minus like that, it would try to run your current the other way. See, that coil is resisting that increasing current. It doesn't like that. That's what the minus is telling you in Lenz's law. Remember Lenz's law? If the current is increasing in that circuit, Lenz's law says there will be a induced current that will oppose the increasing current in the circuit. It acts kind of like a battery trying to push you the other way. We're doing Kirchhoff's voltage law. Let's see, we went from here to here. We've closed this switch now. The switch is closed. And we have our voltage here, and we have minus V equals IR, and we're back to 0. There's your equation. There's your voltage law equation for that circuit. This is called a first order ordinary differential equation. And you study that in a course you take called differential equations. Now let me ask some of you. There's only just a small group tonight. Let me pick on Nicholas. Nicholas, have you had differential equations yet? There's a course called differential equations. The students call it Diffie-Q. Have you had that course yet, Nicholas? Oh, no.
Yeah, I'm in the middle of it right now. So.
You're taking it right now.
Yeah,
You're taking differential equations right now.
I'm trying to.
Well, good. I thought it was hard when I took it many years ago. I took that course. And I thought it was kind of hard. What do you think?
It's really hard.
There you go. Well, let me ask my friend Zach. Zach, have you had differential equations yet?
No.
Not yet, but you know what? You're going to, aren't you? Just say yes, Zach. You're going to have to take it.
Oh, yeah.
Oh, yeah. You're going to take different. Oh, and my friend Phoebe is going to take it too. Phoebe, if you're still able to respond, are you taking it now or are you going to take it? Differential equations.
I assume that if my biochemistry grad program requires it, it'll be something I take in the future. I haven't had it yet.
Not yet. Okay. Well, that's fine. But you've all heard of it. And this is called an ordinary first order differential equations. And I'm not going to bore you with the solution. You could ask your math teacher the solution, but here's the solution. Here's how it goes. The current is equal to now, you've seen this equation before. I know you have. It's similar to an equation that we had for charging a capacitor. Only this is not a capacitor. This is an inductor. But that's the solution where tau is called the time constant, and it's equal to L over R. The name of it is the time constant. Now, I didn't prove to you that this is the solution to that equation, but it is. We could check it out and make sure it's right. That would be fun. But let me tell you about the units first. We know the units for the time constant would be seconds. And we discovered that the units for inductance is ohm seconds. And the units for resistance is ohms. So if you take ohm seconds and divide by ohms, guess what? You get seconds. Yeah. Now here's how I remember this. For a while there, I had trouble trying to remember, well, is it R over L or is it L over R? Well, L comes before R in the alphabet. A, B, C, D, F, G, H, I, J, K, L, M, N, O, P, Q, R. There you go, S, T, U, V, blah, blah, blah. L comes before R in the alphabet, so it's L over R is your time constant. Now, to prove it to you, so that you'll know I'm not lying to you, we'll go ahead and we'll try to prove it. Now, to prove it, we got to take the derivative. See that derivative, that first derivative? Let's do that. There we go. The first derivative of the current Well, these are just constants. That E over R is just a constant. Times 1, that's just a constant. So when you take the derivative of that, you just get 0 so far. And then you have a negative. Well, you'll have that E over R, it multiplies. Then you take the derivative of this, which is e to the minus t over tau. But you have to use the chain rule. You have to take the derivative of this exponent. And the derivative of that exponent is minus 1 over tau. Isn't that how you take the derivative with respect to time? I think so. And so let's see what we get here. What we're doing is we're proving to ourselves that this is the solution to this Kirchhoff voltage law equation. Well, we could simplify that. We got two minuses, and we have E over R times tau, e to the minus t over tau. Did I do good? I think so. I think it's good. Well, that's the first derivative. Now we need to multiply that by L. Okay, we can multiply. Let's write this out. We have E minus L times that, and we've decided that's this. So let me write that. That's E over R times tau. Now remember what tau is. Tau is L over R. And then you have e to the minus t over tau minus IR equals, we hope it's 0. Let's see if it is. You know what? Those R's cancel and the L's cancel. And what we have left is E minus E minus E to the minus t over tau minus IR. I don't get 0 out of that. I must have done something wrong. Let me see now, just a minute. And I'm a little bit rusty at this. We tried to take the derivative of this, and I think we did that right. Yeah. I think we did that right. That's L over R. Okay. And then we did the L over R, okay. Let's see. So we got E minus E over, I got lost. Okay, now just a minute. I'm not quite ready to give, yeah, here we go. I've got E minus L times this. Yeah. But don't we have to multiply by e to the minus t over tau? Yeah, I think we do. Minus IR. Somehow we've got to show that this is equal to 0, and I don't see it. Let me see what happened here. Oh, yeah, here's the problem. I need to plug in this value of I. Not quite done yet. I need some room to do it. And I don't know if there's enough room there. There might be. Okay, here's what I've got. I've got E minus E to the minus t over tau minus I times R. See that R is going to cancel, and here's what you'll have. You'll have an E, 1 minus E to the minus t over tau. hey, look at that E there and that E minus E times 1, they cancel. And you have a minus minus, that makes a plus e to the minus t over tau. And that cancels with a minus e to the minus t over tau. And it's equal to 0. Yay! Kind of stumbled along through there. But what I'm telling you is this is the solution to this equation. And we checked it out and it worked. Okay, well, great. All right, well then I think we could probably work a problem. Let's work a problem. Here, let me make some room here, and we'll do an actual problem. Let's put in some numbers. That's so messy. Let me make something that looks a little nicer. All right, we're going to plug in a problem and try it here. Here's one. Let's suppose you had now this is called an RL circuit. That's what it's called. All right, now let's say this is 6 volts. And I'm making this up. This resistor here, let's say it's 3 ohms. And say that this inductor is 1.5 henries. Okay. Now we're going to throw that switch. We're going to throw that switch, and here's what the current's going to be in the circuit. It's going to be, well, I erased it, but here it is. That's it. Okay. First of all, we have to get the time constant. You tell me what the time constant is. I will shut up and give you a moment to think. And then we'll put the time constant on it. How about it? Let's go to one of my students there. Hey, Phoebe, are you where you can tell us that time constant without endangering your driving?
Well, I'm sitting down and with you now, but I am behind, so I'm trying to catch up, and I don't have this in my calculator yet.
Oh, that's fine. Let's go to my friend Nicholas. Nicholas, what's the time constant?
I don't know yet.
I'll help you here, Nicholas. It's going to be L over R. So you tell me what the time constant is.
Point 0.5?
Yeah, that's what I got. Now, what are the units of a time constant?
Seconds?
Yeah, that's right. It's 0.5 seconds. Good going. So we've made a little progress there. Now this E here that's your 6 volts. That's the EMF, they call it, of the battery. And the R is 3 ohms. So that looks to me like we've got 2. 6 divided by 3 gives you 2. 1 minus e to the minus t over tau, which is 0.5. Now, if you wanted to be fancy-wancy, you could write it like this. I is 2, 1 minus e to the negative 2t. It's the same thing because 1 divided by 1/2 is 2. So we've got our current now. Now, we could draw a graph of that current. Let's do that. Let's just do it right here. We're going to draw a graph of that current. And this is your current versus time. Well, when you throw that switch, t is 0. And so you have e to the minus 0 over tau. Well, that's just 0. E to the 0 is equal to 1. In fact, anything to the 0 is equal to 1, right? So you got 1 minus 1. You got 0. The current is 0. When you throw that switch, right now there's no current anyplace because your switch is open. But when you throw it, right at that instant that you throw it, there's still no current. But it starts to improve like this, and it reaches a peak value. Zach, let me pick on Zach. What is this peak value, do you think, Zach? What will be the current after a while?
How would I figure that out?
You can get it from here, Zach. Put in a big number for t.
Also, would be the current.
Yeah, put in a big number for t, and you can get the current after a while. Put in anything like 5 seconds, maybe 10 seconds, 20 seconds, an hour, whatever you want. What do you come up with? I can wait. I can outwait you guys.
Material through normal means, I went directly to the source.
Zach, when you put in a big number for time, like, see, time is out here starting to get big. Go out here maybe 5 seconds, 10 seconds, 20 seconds. Plug that in there and tell me what you get. Use your calculator if you have to.
I ended up with like 1.9 seconds. So 2 seconds.
Well, we don't get seconds for current. Current is going to be
Or
amperes.
2 amps then.
And this here approaches 0. So you just have 2 times 1 minus 0. You're going to get 2 amperes. You get 2 amps. It's called an asymptote. See, this thing approaches that 2 amp asymptote. Some people call it asymptote. But it's the same idea. I think we need to do it at some actual different amounts of time. Here, let's make a little table, because I want you guys to be able to do this. We're going to make a little table. Is there room over here? I think so. We're going to make a table of time versus current. Now, if the time is 0, the current is 0. See there? When the time is 0, the current is 0. Now let's have maybe 0.25 seconds, 0.5 seconds, 1 second, 1.5 seconds. Well, no, this would be, let's go 0.75 and then 1.0 seconds. We'll go in jumps of a quarter of a second each time. And I'll help you with this one. I'm going to plug in time of 0.25. Okay, here goes. If that time is 0.25, then this equation will be 0.25 over 0.5. And I can do that on my calculator. I can do that. Here goes. Well, I got an answer of 0.7869 amperes. I'm thinking, if I did that right, did anybody else get that? We're plugging in different times here in this equation. See, there's the time. If we plug in 0.25, that's what I get. You try it. Yeah, I think that's right. Did anybody get 0.7869 amperes? Yeah, there's an Good going.
You like the same thing?
Yeah, good. Okay, now plug in plug in a time of 0.5, and I'm going to do it. And let's see what we get for that. I got my answer. I got 1.264 amperes. And see, these are in amperes. These are in seconds. And I'm listening for an on that 1.264 amperes.
Yeah.
Yes.
Yeah. Okay, well, I'm going to shut up and let you do these two. Go ahead. Somebody tell me what this current is at 0.75 seconds.
One 1.5537.
Yeah, you got the hang of it. You're getting the hang of it. Now at 1 second, let's see if we can do that. I'm getting 1.729. Anybody getting that? Say
Yeah.
Yeah, there we go. Now it's approaching 2. We ran out of space right here. We ran out of space. But see, if you plug in, you'll make another little chart here. If you plug in maybe 2 seconds, 3 seconds, 4 seconds, it's going to get closer and closer to 2. Plug in 2 seconds and see what you get. Man, it's really getting closer to 2 now. I'm getting 1.963 Wonder if I did that right. That's probably about when you guys were born, right? If you were born in 1963, how old are you now? No, never mind. You guys weren't born in 1963. You're not that old. Plug in 3 seconds and tell me what you get. What'd you get for 3 seconds?
1.995.
Yeah, there you go. 1.995. We'll do one more. Plug in 4 seconds and tell me what you get. I'll tell you what I got. I got 1.993. Did I do it right?
I got 1.99933. Yeah.
You know what? You know what? You're right, and I'm wrong. I got 1.9993 also. We'll give you a thank you point. You were right. Excellent. Hey, look here. It's asymptotically approaching 2 amps, isn't it? See how it approaches the 2 amps? I think we understand that. Well, good. Excellent. Let's draw a graph of the, I need a little room here someplace. Yeah, get rid of all this here. We got to have some room here to operate. Now you see, that's the graph of the current versus time. Now let me make some more room. Let's draw a graph of the voltage on the resistor versus time. Now you know how that works. The voltage on a resistor is equal to IR. V equals IR. We love that equation. It's got a name even. What's the name of that equation? It's got a name.
Ohm's law.
Yeah, it's Ohm's law. Excellent. Now what it is, it's Ohm's law for resistors. There's a generalized Ohm's law. Oh, gee, I don't know if I can remember that. It goes like this. I can remember it because we had a guy named Joe in our class one year. This is the generalized Ohm's law. It works on things besides resistors, but we're not doing that tonight. That was a while back. You had that, but maybe forgot about it. Let's draw that now. Well, you know what? R is just a constant, so this equation here, or this graph here of the voltage in the resistor is going to look just like that other graph. There you go. It's just that the asymptote won't be 2 amps. What will it be? What will the asymptote be for the voltage on the resistor? I'll let you think about it a minute. I mean, we have the equation for the current. I erased it, but it goes like this. There's the equation for the current. And to get the voltage on the resistor, you just multiply by the resistance.
Is
So,
it 0.7?
what do you think? What do you think this asymptotic voltage will be? Phoebe was going to say something. What do you think that? What's this
Would it be
voltage?
Well,
six?
I'm Sorry, go ahead.
Go
I thought I
ahead.
heard Zach.
We need to know
I was,
what this voltage will be here after a while.
I'm just guessing that it might be 0.7 volts.
No, I don't think that's right.
Okay, I'm completely wrong on my reasoning. Okay, I'm just gonna listen and learn.
Well, that's okay. Look here. If you want to know what happens after a while, how long did we go? About 4 seconds, I think, maybe. You could put in 4 seconds there, and we got the answer. It was dang close to 2 amps. What if you had 2 amps and you have a 3 ohm resistor? What do you get? What's 2 amps times 3 ohms? Anybody know?
6 volts.
6 volts. We're going to approach 6 volts. That's your asymptote. It's 6 volts. And we could make a table of volts in the resistor versus time, and we could just bore you out of your gourds. Of course, at time 0, when you first throw the switch, there is no current. Remember, the current is 0, so there's no voltage, but it increases rapidly. And we have a graph of the voltage in the resistor now. There it is. You could get some more. Here I'll give you one time constant. Now, one time constant is 0.5 seconds. So at 0.5 seconds, I want you to find, whoops, that's in the wrong place. I'll get this right in a minute. At 0.5 seconds, I want you to find the voltage on the resistor. Go ahead. If T is 0.5 and you divide by 0.5, I bet you can do that. Go for it. Tell me what you get for the voltage on the resistor.
.79 volt.
I'm still pushing in buttons. You're faster than me, but I'm getting there. One tiny minute here and I'll have it.
I got 1.26.
Yeah, I did too. I got 1.264 volts is what you'd have. See, one time constant puts you right about here. That's, what is that, a half a second? 0.5
Well,
second?
1.264 is your current, right?
No, that's your voltage. Think. No, you're right.
Same thing that he
He's
got.
right. He's
I
right.
used my numbers from last time.
He's right. That's your current. Proud of you. I'm going to give you a nice thank you point here. You got to multiply that times 3, and you'll get the answer that we have for our voltage on the resistor. I think that was Zach's voice. Zach, did you get 3.793 volts on the resistor?
Yeah.
Yeah. You know what that is? That's 63%. Remember when we did this at one time constant, that's when you get 63%. I don't know, does that ring a bell? We've done this before. Okay, well, let's do it at, let's go way down the road here. Let's suppose you did it at, say, 4 seconds. At 4 seconds, find the voltage on the resistor. All right, I'm doing it. Here goes. Wonder if I did this right. Hey, I'm getting that 1.999 that Phoebe got, but see, that's the current. To get the voltage, you have to multiply by the 3 ohms. And you know what I'm getting? I'm getting 5.9979, blah, blah, blah. See, it approaches 6. That's your asymptote. It approaches 6 after a while. Wasn't that fun? Okay, well, let's do some more. Any questions so far? We're okay? All right. Well, if we're okay, we're going to plot another graph now. Now, let's see. We did the current, and we know how to do that. I probably need to write that equation down so we don't forget it. The current's going to be 2, 1 minus e to the minus t over tau. Now let's plot up the volts on the inductor. Now how are we going to get the volts on the inductor? Well, there's a couple of ways. One way, we could get the volts on the inductor by going minus L di dt.
Hello, Papa.
Hey, bud,
We're home.
how you doing? Hey, good. I'm glad you're home. Excellent. We're just having a fun time in our class here. My students love doing this stuff.
All right, have a nice class.
Okay, bud. Now that's one way to do it. But there's another way, and that is, look, if this is 6 volts, Kirchhoff says you go up 6, and the current's going this way, and so this will be a plus minus. You'll have some volts on the resistor, and then you'll have some volts on the inductor. But hey, didn't we do the volts on the resistor? We just did that. Yeah. We did. The volts on the resistor look like this, and it peaks out at 6. It starts off at 0. There's no volts at all on the resistor. You got 6 volts here on the battery, no volts at all on the resistor. So you know what? This has got to be 6 volts to start with. So let's just call it 6 volts. There you go. What happens is this voltage on the inductor it also has an asymptote, but it goes to 0. It does that. We probably should do a few points. Like at one time constant, we figured the volts on the resistor, it was 63% of 6. It was 3.78. This right here is 3.78 volts. Well, this has got to have the rest. Well, what's 3.78 from 6? I don't know. 2.22? That's what this has got to be. This has got to be, this has to come down a little bit quicker than I drew. This has a value of 2.22 volts. They have to add up to 6. You know Kirchhoff's law. The way it goes is you go up 6. If you drop 2.22, and then you drop what you got on the no. The resistor has 3.78. You drop 3.78, and then you drop 2.22, and you get 0. Does that add up to 0? I think it does. Yeah, that's it. That's one way to get it. You can get your voltage on the inductor at any time you want by doing that. Or you could do it this way. Wouldn't that be sweet? Let's see if we can. Well, to do that, you'd have to take the derivative of this, because that's what that is. Now I use a little I there. It doesn't matter. Big I, little I, there you go. What would be the derivative of that? Well, we did that earlier. You have 2, and the derivative of 2, that's constant. That's just 0. And so what you get, let me write it here. Do we have room? Oh, gosh. I think we got room. You're going to get a minus 2e to the minus t over tau times a minus 1 over tau. Well, the minuses cancel, and tau is 0.5, remember? And so what you wind up, if that's 0.5 in the denominator, didn't we say that it's 0.5? Yeah, I think we did. 0.5. So that makes 4e to the minus t over tau, which is 0.5, or you could just say e to the minus 2t. There you have it. But see, this has, you're multiplying by L. So your voltage, is there room for me to write this? Barely. The voltage on the inductor will be a minus L, which is 1.5 henries, times your 4e to the minus 2t, which gives you a minus, did I do that right? Minus 6 e to the minus 2t. So let's plug in one time constant and see what we get. Now what we got the other way was 2.22. If you plug in a 0.5, then what do you get? Well, I don't know. I'm getting 2.22. Now, what about the minus? I'm a little bit confused about the minus. Well, I get 2.22 minus volts on the inductor. And what they're talking about is this here. It's a drop of 2.22 volts. I got the same answer. I got the 2.22 volts on the inductor. I got it by using this equation here. And I also got it by getting the voltage on the resistor and just subtracting it from 6. I hope I didn't lose anybody on that. I think we need to do some more practice on that to feel good about it. Well, we'll do that at the end. I wanted to talk to you a little bit about power, and then we can practice that some more. Do you have any questions on anything so far?
So it was a negative value because it was a drop?
Yeah. It has to go plus minus because, see, your current is increasing. You see your current increasing?
Yeah.
The inductor has a magnetic flux that opposes that increase. You're trying to increase the current, but if you have a plus minus like this, that is trying to push the current the other way, like a battery would do.
Okay.
It's fighting you.
Okay.
That's what coils do. They obey Lenz's law. Okay. Well, I'm going to talk to you about power for a minute, and then I don't know. I think it's time for a 10-minute break. We probably had enough theory for right at the moment, but we're going to talk about power here when we come back. Go take a 10-minute break, and we'll be back. And we'll talk about power. See, inductors can store power. And we'll talk about that. Go take a 10-minute break. I'm going to go scrounge around in the refrigerator for a few minutes, and we'll be back. Ah. Well, and we're going to talk about power now. I lucked out. My grandson and son-in-law had some pizza. I got a piece of pizza. Trying to think of what kind it was. It wasn't Papa John's. It only cost $5 for the pizza. What a deal. But I can't remember what the, it had a little Roman guy on the box.
That's Little Caesars.
That's it. Little
Yeah.
Caesars. Yeah, it was Little Caesars. Yeah, fantastic. Okay. Plus some breadsticks. Man, I really lucked out. Okay, now the next topic, not that we mastered that one, but we got a start on it anyway. But we want to talk about power and energy. And see, inductors can store energy. They store the energy in the magnetic fields. You know, you can store energy in gravitational fields. Get yourself a heavy object and lift it up high, and you're storing up energy. Go get a big stack of books and pick them up off the floor and set them on top of your table there. You just stored some energy, gravitational potential energy. And we've learned that you can store energy in capacitors. In fact, with a capacitor, I don't know if you remember, the energy, your book uses a U. It uses a U for energy, and the energy stored in the capacitor is 1/2 CV squared. But the energy stored in an inductor, and I want to show you how they got this, is 1/2 Li squared. Let's just look at the units for just a minute, and then we'll show you where that comes from. You know the unit of energy is the joule. The half is dimensionless, so we don't need to worry about the half. That's a Henry there. That inductor is in Henrys. And it looks to me like you've got amps squared here. Well, do you remember that a Henry is an ohm times a second? So here, write this as ohm times a second times an amp times an amp. How's that? Did you know that an ohm times an amp is a volt? So what we have here is a volt times an amp times a second. I don't know if, I hope I didn't lose anybody. But see, an ohm times an amp is a volt. Remember, V equals IR. An ohm times an amp is a volt. Ohm times an amp is a, so we got a volt. There's an extra amp there in a second. I don't know if you remember this, but volts times amp is power. P equals IV. We've had that equation. And so what we got there is power in watts times seconds. Well, what's a watt? A watt is a joule per second. And if you take a joule per second and you multiply by seconds, you get joules. Yay! It took us a while, but the units seem to work pretty good. That works pretty good. And now let's show you where they got that equation. The units work good, but that doesn't really tell you how they got that equation. So let me write one of these LR circuits here again. Okay, we've got a resistor, we've got an inductor, and we have a battery. And we're going to go around this circuit like we did before and do our KVL. There we go. We're going to go from here to here. Well, that's a plus. And then from here to here, that will be a minus. And remember, it's trying to oppose that battery. Whenever you put plus to a plus, you're opposing. And then here comes the current going around here counterclockwise. And there's your KVL. Now we're gonna do a little algebra trick here. Let's use little I instead of big I. Algebra wise, you can multiply everything in an equation by the same thing, and algebraically, you haven't heard anything. What I did was I multiplied everything by little I. That's legal. Well, this is current times voltage. You know what that is? That's power. I squared R, you should recognize that. That's power. Well, if that's power and that's power, well, then this must be power. Here, let me write that. Power in an inductor is IL di dt. Another way of thinking about power is it's equal to the rate of change of your energy with respect to time. That's what power is. It's joules per second, watts, right? So get rid of the dt's here, and what you have is du, which is energy, equals I L di. Or let's write it L I di. There you go. Now let's integrate that from 0 to some value of power that we're going to store up. And we'll integrate this from 0 to some final value of current. Now, when you integrate this, you know what you'll get? You'll get 1/2 Li squared. It's kind of like if you had a constant times x dx, and you integrated that, you'd get 1/2 kx squared. Ring any bells? Well, this is going to be the integral of Li di. You get 1/2 Li squared. There you go. You can make that a capital I if it makes you happy. And when you integrate this, you'll just get your total energy stored up. Hey, we just came up with the equation for power storage in an inductor and the energy storage in an inductor. And now we could take an inductor. We have some in the lab that are 22 henries. They're kind of a heavy little thing. It's about the size of your fist, and they're 22 Henry inductors. They're kind of heavy because they got all these wires wrapped around. And let's suppose you ran, I don't know, make something up here, 5 amps through them. You run 5 amps through them. Okay, I'm going to shut up now, and I want you to find the energy stored in joules if L is 22 henries and I is 5 amps. I'm going to shut up. Find the energy stored in that inductor.
What do we call L again?
L is called inductance. Thanks for asking. It's an inductor. Go ahead and plug in L, 22 henries, plug in I, 5 amps, and tell me what you get for the energy stored in that inductor.
275 joules.
That's what I got. I'm getting 275 joules. It's kind of weird. It's energy stored in the magnetic fields. Now, I want to tell you something about inductors. You can't change the energy instantaneously. Let me make some room here to talk about this. It's sort of like with a heavy stack of books, okay? If you have a heavy stack of books and you lift them up and you put these up on top of the table, you can do it pretty fast, but they don't go up there instantly. You have to grab them, you have to lift them. It takes a little bit of time, maybe 1 second. Let's see. I'm gonna reach down. 1001, 1000. There, I got them. But see, it took me what, about a second and a half. Energy doesn't jump from one place to another without some time involved. What I'm trying to tell you is the current can't jump, because if it did, if the current could go from 0 to 5 amps just at the snap of your finger, it can't do that because energy can't jump like that. It takes time to change your energy. See, remember when we charged this thing up, we plotted the current. Here's the current, here's time. When we threw this switch, it didn't just jump up. I forget what we had here. Was it 2 amps? I don't remember. 3 amps, whatever it was. But it didn't go from zero to whatever this is. Let's say it's 2 amps, okay? It didn't go from 0 to 2 amps instantly. It took a while. See, one time constant, you got up to, what was it, 63%. What did that take? A half of a second on our thing that we worked out? It doesn't just jump up like that.
Well, what if you took the resistor out of the circuit?
Oh, no, that's a lovely thought. That's very intelligent. If you took the resistor out, let's see what the time constant would do. The time constant is L over R, right? And if the resistor is 0, what's L divided by 0?
Well, you'd still have the resistance of the wiring.
Yeah, that's
So,
true. You'd still have resistance of it. Wouldn't be 0.
yeah.
You couldn't get 0. That's
Be
kind of
super,
bothering me
super
because
small.
the time constant would be very big, wouldn't it?
Yeah.
I would think it would be smaller. How come it's very big? I wish you hadn't asked that, Zach. Now you got me all confused. I was doing great up until now. But if you took the resistor out and just made this a straight wire and through that switch, well, let's look at the volts on the inductor. You know how they go. The rate of change of your current, I would think, would be a lot faster because the resistor's out of there. You still have resistance of these wires. It's not really 0. But I don't know. I'm going to have to think about it. Good going. You stumped the instructor.
Sorry about that.
Yeah, good going. But let me tell you about capacitors for a minute. I don't know if I've told you this, but the voltage can't take a jump here because, see, with capacitors, the energy stored in a capacitor is 1/2 CV squared, and it can't just jump instantaneously, so that the volts can't jump. Now with an inductor, the volts can jump. They can go from 0 to a 10 volts or whatever, just at the snap of your finger, but capacitors can't. But with inductors, it's the current that can't jump. The current can't jump. Let me tell you what inductors are like. Inductors are like in my garage, I have a flywheel. It's a flywheel, and well, it's really a grinder, okay? And I turn it on, and it spins, but it takes a second or two to get the speed up. I turn my switch on, and this grinder goes like that. When I turn the switch on, it doesn't go immediately. It has to go, you turn the switch on, it goes, you got it? It's a flywheel. It's a flywheel, and it takes time. See, it takes time for that current to crank up and increase your energy storage. It doesn't just give you that energy immediately. And the same thing when you turn it off. When you turn that flywheel off, it doesn't just stop instantly. It goes like that. It takes it a little while to stop because there's a lot of energy stored in a flywheel. Now, this is not electrical or mechanical, or it's not energy stored in a magnetic field. It's energy, mechanical energy, stored in a spinning flywheel. It's mechanical energy. It's kinetic energy. It's 1/2 mv squared. It's kinetic energy. I'll tell you something about energy. Look at here, 1/2 CV squared, 1/2 Li squared, 1/2 mv squared. There's sort of a pattern there, isn't there? When you run across something that's 1/2 something times something squared, you're probably talking energy. Okay, well, great. Well, that was a lot of fun. I told you about inductors. Let me show you the inductance of a solenoid. Let's do that next. The next thing we're going to do, I talked to you about power. We developed the equation for it. And now we're going to talk about the inductance of a solenoid. Remember all those things that when we started our class, I gave you the magnetic field of a straight wire, magnetic field of a solenoid, toroid, short wire, circular loop, etc. Well, we're going to talk about a solenoid right now. And we're going to talk about the inductance of a solenoid. Okay. Well, we have an equation for inductance, and it goes like this. We developed that equation earlier. If you forgot where on earth it came from, When my daughter gets the video on YouTube, you could re-watch it, but we showed you that. And what we're going to do is we're going to do it for a solenoid. Now, for a solenoid, you know what the magnetic flux is. It's the magnetic field times the area of the solenoid. By definition, that's what magnetic flux is. And we have an equation for that. It goes like this. Put that A on there. And we're on our way here. Let's plug that in here, and we'll be almost done. Hey, look, the i's cancel. We can get rid of the i's, and what you have is mu sub O n times little n times A. Okay, did I get everything right? I think so. Now, do you remember little n? What that is the number of turns per length. So you could write this as mu sub O big N times big N over the length times the area. Well, that should be it. That should be the inductance of the solenoid. Now let's see if I got that right. Just a minute here. Let me shop around here and see if they have that. Help me find it. It's in this chapter someplace, I think. Inductance of a solenoid. I don't see it. Okay, well, let me keep looking. I'm not going to give up yet. I'm looking for the inductance of a solenoid. Hey, there it is. Look at there. I'm on page 643. Page 643. The inductance of a solenoid is mu sub O n times n, or n squared, area over length. Okay, well, let's do an example of that. Need a little room here. Here's our equation. It's on page 643. Suppose you wanted to make a inductor. Go get yourself a, well, I don't know, a piece of wood, a dowel maybe. You get yourself like a pencil even. You could take a pencil or you could take one of these dry eraser markers. That'd be all right. And come in here and wrap some coils around it. Wrap some coils around it. Let's say you wrapped 50 turns. N is 50 turns. And suppose the length of this is 10 centimeters. We're making our own inductor now. See, if you get stranded on a desert island someplace and you need to make a radio and you need an inductor, radios have inductors in them. I'm showing you how to make one. Now, L is 10 centimeters. So let's see what we got. We got the L. We got the N, so you go N times N. And now the area. Well, I don't know. It's got a diameter of 2 centimeters. So we can get the area, and you know mu sub 0. Hey, we got enough, we can find the inductance. I'm going to shut up now, and I'm going to see if you can do this. we know what that is. And the N, we know that. We know that. The area, you can get it if you have the diameter of the wooden dowel there. And the length, yeah, okay. I'm going to be quiet. You have a minute and a half. Find the inductance of that inductor. It's a solenoid. Go for it. I'll be quiet. Well, I've got an answer. I don't know if it's right. I'd want to go back over it a few times. Any of you would like to tell me what you got?
I got 3.9478.
3.9478. What's the units? Gotta have units. Everything has units. What's the units for inductance?
Is it ohms per second?
Say that again, please.
Is it ohms per second?
No, it's not. It's ohms times seconds. You almost had it, but the fancy word is henries.
Henry's.
Yeah,
Okay.
but that's not what I got. I might be wrong. You might be right. Somebody else, give me an answer. Somebody else. We're writing down answers.
Well, I got that times 10 to the negative fifth.
Oh, good for you. Good for you. That's still not what I got, but you're closer. You're getting a lot closer, and it might be right. Anybody get a different answer?
Yeah, I got 9.86 times 10 to the negative 6.
9.8. Say again, 9.8 what?
9.87, basically.
Times 10 to the minus 6 henries?
Yes.
Well, that's what I got. One of us is probably right. Let me write this out here and we'll see here. Or you could say it's close to 10 microhenries, couldn't you?
Yeah, I guess so.
Yeah, you could. Okay, well, let's get the area first of all. Now the area is going to be pi r squared, right? Pi r squared. If the diameter is 2 centimeters, the radius is 1 centimeter. So we can get the area. And n is 50. And it doesn't have any units. mu sub O, we know what mu sub O is. And the length is 0.1. So if you write all that in there, here's what you'll have. You'll have mu sub O 50 squared pi 0.01 divided by 0.1 meters. And I think you get the 9.87. You could say micro henries if you wanted to. Okay, good going. Anybody else get that besides just me and Phoebe?
Yeah, I got that.
Yay, good going. Excellent. Well, we can make our own inductor. Now, if you ever take apart a radio, they have inductors. They're vertical like this, and they have this little iron core, and it's got it's like a screwdriver slot. You can take a screwdriver and you can move that iron core in and out and adjust it, and you can adjust the inductance of your coil. Do you remember that if you have a solenoid and you put an iron core in it, it increases the inductance. It increases the magnetic field. We studied that for sure. It increases the magnetic field, and you can adjust it. But you don't want to use a metal screwdriver. They have special plastic screwdrivers that you can turn that iron core in your inductor. They use that to tune your radio. Interesting. Okay, well that was loads of fun. Let's work a few problems in the book now. All right, I'm going to find some problems in the book. Go to page. We're going to do. Hey there, how's it going? We're going to do 1435, and this is on page. I need some room here. We had a lot of fun doing that. And then make your own inductor thing. I'm on page 663. And we're going to do problem 1435 together. Okay, they said an EMF of 0.4 volts. Let me write this stuff down. EMF of 0.4 volts is induced across the coil when the current through it changes uniformly from 0.10 amps to 0.60 amps in 0.3 seconds. See, what they're doing for us is they're finding di dt. Okay. And they want to know what the self-inductance of the coil is. Well, here's the equation. If you know this, and they give it to you, and you can find this, and I think you can find the inductance of the coil. So go ahead and find what this di dt is. To make it simple, go delta I over delta t. That'll work. We know we can find the change in, see, these are amps. The change in your amps from 0.1 to 0.6 would be 0.5, and the time is 0.3 seconds. So go ahead and find the inductance on 1435. I'll shut up for 45 seconds. Go for it. Well, I got a inductance. I got 0.24 henries. Did anybody get that?
Yeah.
Yeah, we did good. Now, don't get confused about that minus sign. That minus sign is there for Lenz's law. Remember Lenz's law? And Lenz's law says that the induced current caused by the changing magnetic flux will oppose the change in magnetic flux. And we'll show you that again here in a little while. We'll do another one of those LR circuits. How about the rest of my wonderful students? We're doing okay on that 0.24 henries? I need to hear an uh-huh.
I just had solved for the wrong thing, so yeah.
But you're okay now?
Yes.
Okay. Well, let's do another problem. Oh, wait a minute. Let's see how we did. Let's check the answer book. Go to the back. We're looking at problem 1435. And they said 0.24 henries. Yay, that's what the book says. So we did great. Let's do another one. All right. Any comments or questions? All right, well, let's do another book problem. Here we go. This one's also on page 663. It's problem 1437. Problem 1437. And it says, what is the rate at which the current through a 0.3 Henry coil is changing if an EMF of 0.12 volts is induced across the coil? Well, here, let me write some of this down. The EMF is 0.12 volts. And we've got an inductance of 0.3 henries. Okay. And we have a lovely equation. It goes like this. It's very similar to Faraday's law. Remember, Faraday's law goes like this. And this is very similar, isn't it? We talked about that earlier. Okay. Now let's see, we know this. And we know that. And I think this is what they're asking for. They're asking for what is the rate at which the current is changing. They want to know dI/dt. I'll shut up. You have 30 seconds. I'm going to see if I can get this right. Go for it. Well, I got my answer. I'm getting a rate of change of your current. Well, what did you get? Why should I have all the fun? What did you get? We're solving for the rate of change of the current. I'll pick on Zach. Zach, what'd you get?
0.4
That's what I got. Now, what are the units on that, Zach?
amps.
No, you're close, but it's not amps.
Amps per second.
Yes. It's 0.4 amps per second. Now let's see how we did. 1437. I'm going to go to the back. We're going to see how we did on that. 1437. I don't see it. Here it is, 0.4 amps. Yay, that's what the book got. Again, we did great. Hey, did OSU win their football game this past week? Anybody know? I need to ask my
No, I
daughter.
don't know.
I don't know either.
I think I heard they did by a little bit. I don't know the score. I'm sorry.
I'll have to ask my daughter. She graduated from there. She graduated and makes more money than I do. I'm proud of her. Okay, well, let's do another one. We're doing great. And then we'll do an RL circuit. Okay, now this one is I don't want to do that one. I want to do an RL circuit. Here we go. We're going to do an RL circuit. That means you have a resistor and an inductor. And here's my circuit. Three ohms, 6 henries, and 3 volts. It's an RL circuit. There's your L, there's your R. We're going to throw this switch, and what happens is the current is going to start going, wait a minute, it's going to go clockwise this time, isn't it? There's a plus, there's a minus. The current is going to go clockwise this time. And when you throw that switch, the current just can't jump from 0 to some value. It takes time to do that. And first of all, we need to know what the time constant is. I'll shut up for a tiny minute, and I need you to tell me what the time constant is. What is it? If you've forgotten, it's L over R. So what is it? What about my friend Nicholas? I haven't picked on you for a long time. Nicholas, what's the time constant?
2 seconds.
It's 2 seconds. Good going. Okay. Well, here let's make a graph. I think it'd be fun to make a graph. of the current versus time. And a graph of the voltage in the resistor versus time. And a graph of the voltage in the inductor versus time. Now I'm going to shut up for a minute, to maybe 2 minutes, maybe 3 minutes, because you might have to think about these just a little bit, but we need to know how to make these graphs of the current versus the time. It might help you if I gave you this equation. Maybe that'll help. There's your equation. I'm going to shut up. I want to see if you can make those graphs, or at least that one. So see if you can at least make that one. I'll be quiet and give you some time. Go ahead. Well, I gave you a little time to think about it. Do you remember what the shape of this thing here looks like? It looks like this. It starts at 0 because remember, the current can't just take a jump from right now. When this switch was open, and we had an open switch here, when it's open, there's no current at all. And when you close it, and you close that switch, the current right at the start will be 0, but then it builds up and becomes a constant. And after a long time, this term drops out, it becomes 0, and you get whatever that maximum voltage is. Or I don't mean voltage, you get the maximum current. This is wrong. Guys, this equation's wrong. This needs to have the maximum current. Somebody could have gotten a thank you point for that. What is this maximum current here? Does anybody know what the maximum current is going to be? Phoebe, what about you? What do you think the maximum current's going to be on this?
I'm really not sure. I'm kind of confused on that. I'm
I'm not
sorry.
either.
Well, here, let me show you what's going to happen. You know the voltage on the inductor is equal to minus L di dt. Well, after a long time, the current is constant, and the derivative of a constant current is 0. So after a while, you could just make a short here. You just have 3 volts battery, 2 ohms resistor, so you get 2 amps. You get 2 amps. So the maximum current will be 2 amperes. You can plug in some numbers if you want. If you make this time big, this term goes to 0, and you just have a constant current. And how big is it? Well, there's no voltage here. There's no voltage because the current's not changing. You got to have a changing current. See, with an inductor, you have to have a changing current to get voltage. If the current doesn't change, no voltage. All the voltage will appear across the resistor. In fact, when you throw that switch, after a long time, the resistor will have 3 volts on it after a long time. It's going to do this. It's going to reach 3 volts. And the equation for the resistor is going to be like this. Same equation. Does it make sense that the voltage on the resistor is equal to IR? And if the I is doing that, and R is just a constant, then the volts on the resistor is doing the same thing. And it will be 3 volts at the end. But what will the voltage be on the inductor? That's a good question. When you first throw the switch, what will be the voltage on the resistor? You guys tell me. When you first throw the switch at time 0, what will be the voltage on the resistor?
Zero.
It's 0. It's 0. You don't have any voltage on the resistor. Well, you got 3 volts on the battery, so that must mean that you have 3 volts on the inductor. So you're starting with 3 volts on the inductor. It's not 0 when you first throw the switch. And then what happens with the inductor is the voltage on the inductor tapers off and approaches 0 asymptotically. There's your 3 equations. Here, I can write them.
I don't understand where the 2A is coming from.
Say that again, please.
I still don't understand where the 2 amps is coming from.
The 2 Fs.
2 amps.
Oh, the 2 amps. Thanks for asking. The 2 amps. Well, we have, because it's wrong, that's why. We have another honkin' thank you point. If you have 3 volts and 3 ohms, you don't get 2. You get 1. Hey, do you feel better now, Zach?
Yeah, that's better.
Yeah,
Yeah.
you were right. Zach was right. I was wrong. I think you guys learn more when I goof up than when I do it right. But it's 1 amp, and that's your That's your current after a while. Now, did I get this right? The voltage on the resistor,
Yeah, I believe that's right.
I think I got that right. What about the voltage on the inductor?
That seemed right.
Yeah,
Or is it two?
I think that's right. Yeah. Okay. There's the equation for the voltage on the resistor, and here's the equation for the voltage on the inductor. It's equal to this here. It's a different equation. This is called a exponential decay. It's an exponential decay. You need to become familiar with these three graphs. Okay, well, great. Well, that was a lot of fun. Now we could ask you for specific values at a specific time, like maybe, how about 1 second? Let's find, I'll give you guys a little project here. See if you can find at 1 second, when we throw the switch, and the current does this, at 1 second, find the current, find the voltage on the resistor, and find the voltage on the inductor. I'll shut up and I'll give you another chance to work, and then we'll do that. Find the current and the two voltages at 1 second. We got the equations, just plug them in. Well, how about it? Maybe pick on Nicholas again. Nicholas, what'd you get for the current at 1 second?
Uh, 0.3935 amps.
That's what I got. That's exactly what I got. Hey, since you did so well on that, Nicholas, what'd you get for the voltage on the resistor?
1.18
What
volts.
I got. Now that sounded like Zach's voice. Was that Zach?
No.
Hey, you
No,
guys
yeah.
you got voices that are just alike. So there's the voltage on the resistor at one second. Now what's the voltage on the inductor at 1 second?
1.8196.
That's what I got. Yeah, I think we're maybe starting to get the hang of this. Yeah, we did great.
Can you at least work the first one, the current one, because I'm not exactly sure. I'm not finding
Here,
it.
let me plug in the numbers. Here we go. Here's the equation. The maximum current is 1 amp. So,
Okay, I got it now.
you got it.
I'm not sure what to use for the current, and I was
Yeah.
messing with.
Good going. Now, back to Nicholas. Nicholas, there's two ways of getting this voltage on the inductor. You can use this equation here, or you can just subtract what the resistor's voltage is from the 3 volts on the battery and get it. Which way did you do it? Do you remember?
I plugged it into the equation.
Yeah. Oh, I see what you did. You plugged in this equation, didn't you?
Yeah.
Yeah, there's nothing wrong with that. Nothing in the world wrong with that. That's the equation. But see, you could get it like this. Look, if the resistor is 1.18, take 1.18 and subtract it from 3.00. Because see, they have to add up. And you get 2 and 1.82. Look, 1.82. It works, see? You can do it that way. Excellent. Well, we did great. Now, now let's suppose that you let this thing run for a while, and right now we have 1 amp running through it, and we have the voltage on the resistor is 3 volts. Here, let me draw it for you. We know right now that we have 3 volts on this resistor, plus minus, because the current's going clockwise. And we have 0 volts on the inductor. This is after a long time. After you've left the thing, you close the switch and you let it run for a while. The current's not changing. We've reached that asymptote, right? And the current is 1 amp clockwise. You got 1 amp clockwise. The current's not changing here, so the voltage on the inductor will be 0 because the derivative of a constant is 0. The current's not changing. It reaches that asymptote 1 amp. So you got 0 volts on the inductor, 3 volts on the resistor, 3 volts on the battery. See, they're button heads, plus, minus, minus, plus. Go around the circuit, KVL, and you get 0. Great. And here's what we're going to do. We're going to take the battery out. We're going to have a switch here. And this switch was right here, remember? It was right there. And we're going to take that switch and we're going to connect it to here. We're going to take the battery out. The battery's gone. The battery's out of there. And what we need is we need the voltage, we need the current. We need the graph of the current versus time. See, it'll be 1 amp the instant you throw that switch, but it's going to change. And then we need the voltage on the resistor with respect to time. And then we need the voltage on the inductor with respect to time. See, the battery's gone now. When you start out, the current will be 1 amp. Here, I'll mark it. It's 1 amp when you throw that switch. And I can tell you what the voltage is on the resistor. If the current's going like this and it's 1 amp, won't that be 3 volts? You'll have 3 volts on to start off with. What about the inductor? Well, if this is plus minus, this has got to be minus plus. You probably should draw it like this. You got the minus 3 volts in the inductor. So we've got all of our starting values, and we're going to draw the graphs, and we're going to write the equations. Now I'm going to shut up for a minute and a half or whatever, and I want you to try drawing what you think is going to happen. See, the battery is no longer a factor. We've gotten rid of it. You can just erase it if you want. Forget it. The battery's gone. We're going to have what do they call it? The exponential decay. The current's going to die out because the battery's gone. All right, I'm going to shut up and see if you guys can write those graphs for me and the equations. Go for it. Well, I gave you a little time to work on it. You're going to have an exponential decay. Your current's going to be 1 amp when you first throw that switch, but it's going to die out and approach 0. It'll approach an asymptote of 0, like that. And the equation for it looks like this. Where tau, remember, we did tau, it's equal to 2 seconds, isn't it? Isn't that what we said? L over R, 6 over 3 is 2 seconds. Okay, that's what that looks like. Well, what's the voltage on the resistor going to be? Well, the voltage on the resistor is just equal to IR. V equals IR. So it's just a constant times that. The constant will be 3. So it starts off at 3 volts. And it does the same doggone thing. It dies out and approaches 0 asymptotically like that. And what does the equation for that look like? Well, it looks like this. But now what does the inductor look like? Good question. Well, see, these two have to add up to 0 because there's no battery. it's going to look like this. It's just equal and opposite the voltage on the resistor, because they have to add up to 0. And your voltage on your inductor equation will look like this. I hope you got some of that. Let's do it at a particular value, and then I think we're going to run out of time the way the clock is ticking. What about at t equal 1 second? At t equal 1 second, what is the current?
You getting that 3 in front of the equation from the resistor or from the volts?
It's 3 volts.
Yeah, that,
Because you have 1 amp and 3 ohms, V equals IR, you get 3 volts on the resistor. And the 3 volts here has to equal the 3 volts here, because they're opposite, but they have to add up to 0. Did that make sense? They have to add up to 0. Look,
yeah,
if you
yeah, I get that.
do KVL, that's 3 volts. Then this is the opposite 3 volts. They add up to 0. Now here's what I want you guys to do. I want you to find the current at 1 second. Find the voltage on the resistor at 1 second. And find the voltage on the inductor at 1 second. And I'll be quiet. And I want to see if you can do it. Go ahead. Find the current at 1 second. I know you can do it. Well, I did that, and I got what I think the current is. See, 1 second will put you right about here. 1 second. I'm getting 0.6065 amperes. If you got that, say, uh-huh.
Yep.
Yay, yay, yay. Excellent. Now to get the voltage on the resistor, V equals IR. Just multiply that current times 3. And I'm getting 1.819 something volts on the resistor.
Yep.
Yes.
Great. Now to get the voltage on the inductor, well, it's equal and opposite. So it'll be a minus 1.819 volts. I don't have to use this equation at all, but let's do it just in case. We're going to plug in this equation and see if we get that answer. Here we go. I'm plugging it in now to see if it works. Here it goes. All right, I'm plugging it in. Boy, Jove, That's exactly what I get when I plug in this equation, but I didn't need it because I knew these had to be equal and opposite. Do you feel good about that one? Now, see, we could ask you any time at all. We could ask you when time is equal to whatever, you name it, 0.75 seconds. What's going on then? Well, we could figure it out. You got the equations. You know what the graphs look like. One last question. I didn't ask you this, but when time is 1 second, what is the energy? They use a U in this book. If I was doing this, I would say it's potential energy. It's magnetic potential energy, but they don't like the way I think. Find the energy stored in your inductor at the time of 1 second. I'll shut up. You have a minute and a half. Find the energy stored in the inductor when the time is 1 second. Can you do it? I bet you can. How about my friend Nicholas? Nicholas, do you have that yet? Do you have the energy stored in the inductor at 1 second after you throw that switch? Earth calling, Nicholas. Come in, Nicholas.
I got 1.1035 joules.
I'm so proud of you. I'm so proud of you.
Did I get it right?
That's right.
All right.
What are the units, though?
Joules.
By Jove, he's going. Do I need to help anybody on that or not?
Nope, I got that too.
I
And
got it.
yay, we're winners. Okay, guys. Thursday night, I've put your lab on Blackboard. Study it so you won't come in and not knowing what we're doing. And we'll have a lot of fun as always. This is your 10th lab. All right, I'll see you on Thursday night for more fun. And here's your last chance to say anything. Speak up or I'm going to push this red button.
Have a good evening.
Hey, you too. You guys have a great evening.
Thank you.
You're a great
Bye.
class. Bye. Bye-bye.
Bye.